Hello, everyone. Welcome to today's sharing session on developing medical imaging application across GPU, FPGA, and CPU using oneAPI. This is Scott Wang. Together with my colleague, Wang, we will deliver this training. The following colleagues also contribute to this project. Within the next 30 minutes, we will introduce the project background, code migration, beamforming implementation, and optimization on Intel GPU and FPGA. We will also have a session to discuss the results. Now, let's look at the project background. So what is Supra and why we need it? Supra is an open source project to develop a software-defined ultrasound processing for real-time application. The GitHub repository is at this link. Medical ultrasound is a popular diagnostic device used in hospital to check human body. Sound waves are transmitted to human body, and its reflection is picked up by receiver and processed by specialized hardware. Original Supra project is based on CUDA programming language. Our project port and optimize the beamforming code onto Intel GPU and Intel FPGA using oneAPI programming framework. Now, we can look at software beamforming. Originally, popular ultrasound implementation will use FPGA to do beamforming and its respective hardware programming language to program this algorithm. There are more trends to use high-level programming language such as C++ and the GPU to implement this algorithm. In our context, software beamforming also refers to use oneAPI with data parallel C++ to program FPGA. Now, I will ask my colleague, Wang, to introduce the project details.
Thanks, Scott, for the introduction. Hi, everyone. I will introduce the code migration, optimizations on GPU and FPGA of beamforming algorithm. Let's get started. As you may know, Intel oneAPI provides a data parallel compatibility tool to help developer migrate existing CUDA code to oneAPI code. The basic migration flow is that DPCT will take a CUDA code and input and migrate its language property to DPC++ code. Currently, the tool can migrate about 80 to 90% of CUDA language to DPC++ code. In our case, nearly 89% of CUDA language features were migrated successfully. It will also add comments into migrated files to help developer manually modify code to complete migration and achieve better performance. In our project, we totally migrated 28 files, and it only takes minutes to finish the whole migration. It usually saves a lot of time for us. DPC++ is a quite a new language for most of us, but it's difficult for C++ programmer to pick it up quickly. This table is a summary of APIs in migrated DPC++ code. Most of these APIs are quite easy to understand. For developers who know concepts of OpenCL, it will be easy to understand the expression of parallel directives. Here are some examples of which we need to manually modify the code. The first one is a CUDA event object migration. The DPCT tool assumes the CUDA event object is used to measure the CUDA kernel function time and and it migrate CUDA event to SYCL event. It also and C++ time measurement library API. In our case, we don't use these APIs to measure time, so we just remove these APIs. The second example is to create streams in CUDA. In DPC++, the stream concept is replaced by the SYCLcon. We also need to modify the migrated code to make sure create a SYCLcon with correct property. For now, the CUDA thrust library can't be migrated by DPCT, so we need to rewrite the thrust related APIs. The DPCT will also insert comments in the migrated code to remind the developer to modify thrust related API. The list are the examples of successfully migrated APIs. The three of the APIs are used to allocate CPU memory, shared memory, and GPU memory. All these APIs are migrated successfully and now need to modify. Now let's look at the code migration on the Intel GPU. We will first introduce the beamforming algorithm and then give some optimization tips on GPU. These figures shows the basic principle of the ultrasound imaging model. The finger in the left shows the one pulse echo process for the sensor ammo. The time it receives the reflected ultrasound signal is T plus R and divided by C0. C0 is the average speed of sound travels inside the body, and for each sensor, the delta T is difficult due to its different location. So let's look at the right finger. For one reflect point, we need multiple sensors to receive signal from it. So each sensor's input should be summed up. Before we sum up all the sensors' input, we first should align the signal from each sensors, and this is the basic principle of the delay and sum, which is the most widely used algorithm in beamforming. In our project, we process the input signal in offline way. That means the input data were captured and saved in disk, not received from sensors directly. The input data is stored in a three-dimensional way. This picture shows the data used to produce one frame of the output beamforming image. The beamforming delay and sum algorithm can be implemented in single thread method. It's a nested for loop. The outermost for loop iterates over scanline number, which means how many pulse echo process in an image. The second for loop iterates number of samples, which means in a pulse echo process, how samples were captured. For the innermost for loop, it calculates 1 pixel of the output image. We can see that the outermost and the second for loop represents the column direction and the row direction respectively. And most importantly, these two for loop can be calculated independently. This means we can do parallel computation in GPU. This picture shows the original beamforming implementation on GPU. As you can see, each work item calculates 1 pixel in output image. The picture shows how the first column was calculated. Inside a work item, the programmer still needs to iterate over channels to calculate the delay value, fetch raw data according to the delay value and the sum data. This iteration can be further optimized. The first optimization is that we calculate 2 pixels in a work item, and we use SYCL vector to reduce the delay and sum iteration number. First, we use SYCL vector to do manually vectorization to calculate 8 delay values and fetch 8 data in a single iteration. This is the optimized code of using SYCL vector. The second optimization is that we use SYCLcon directive to fetch multiple data once. The original function call only fetch and return a single float data. After optimization, we can fetch 8 float data each function call. We also use the cache to improve performance. Before the kernel function starts, we copy the failed data into GPU memory. This can increase the cache hit rate during data fetch. We can also use the return to help us. For the optimization tool, we use the return to look at the detail. It shows the cache miss rate get down after the optimization. The last optimization is using ECMD directive. For the delay and the sum, we can use ECMD to rewrite the kernel function. The main idea is that in each work item, it calculates more pixels in output image. In our case, it's calculated 32 pixels in one work item. This method reduces the number of work items and increase the cache hit rate due to memory access method. Now let's look at the beamforming implementation on FPGA. The migrated DPC++ code can also target to FPGA with the rewrite of kernel function. The FPGA code were tested on Intel Dell Cloud with Area 10 FPGA, and you can see compared to GPU, FPGA can achieve better performance for beamforming algorithm. Now let's look at the code detail of the FPGA implementation. The first thing we do is to shuffle the raw data store pattern. The store pattern method is still three-dimensional, but we exchange the sample and channel order. The picture shows the data store order before and after shuffle operation. This picture shows the computation pattern of FPGA implementation of beamforming. The main idea is that we use 2 local buffers to load and a new scanline data in the ping-pong manner. For example, for the computation of the first column in the output image, we use the buffer to fetch raw data and do delay and sum operation. In the meantime, we load the next scanline data into the idle buffer. When the first column calculation are finished, we then use the idle buffer to calculate the second column, and we load the third scanline data into the used buffer. In this way, we calculate the output image column by column. The right list shows the beamforming algorithm description. There shows the same code of the GPU and the FPGA. We can see that the FPGA code is also written in high-level language and some Intel extension. This gives a powerful tool for software developer to program the FPGA. Okay, the code detail part is finished. Let's go back to Scott. Thanks.
Thanks, Yong. Now I will briefly go through the result and the analysis section. And the video I started is the Supra user interface. You can have a direct view on the beamforming result of the ultrasound image all the way from the raw data. This is on the screen. There is a logo. There is a Lego under the water. You can see the image is getting clearer from the left to right. Meanwhile, we have tested the code on Intel Dev Cloud. You can have the link here, right? For those that don't have FPGA hardware, Dev Cloud can offer a quick testing environment. For GPU code, welcome to try on the PC that come with you handy on your desktop or laptop PC. Here is the screenshot of the Python Jupyter notebook that we guide user to download and build and run the FPGA beamform code on Dev Cloud. For those, you can actually try the FPGA beamforming code on Dev Cloud. For Supra, the key performance factor is the total time to process one frame of beamforming. In this table, you can see we listed 4 Intel hardware, UHD 630, Iris Xe, and DG1 and Area 10, and their performance for the 4 beamforming stages. A note worth taking is for FPGA, we can do hardware pipelining of the 4 processing stage. The longest stage will be the effectively average result of the 4 stages. In this case, for A10, it will be 5.94 milliseconds per frame. Then for GPU, DG1 is the latest discrete GPU released by Intel. It outperforms the CPU graphics in UHD 630 by almost 2 times for this specific workload. Now we came into the summary page. So oneAPI is a unified programming framework or language, including the language, to implement a medical algorithm acceleration on various Intel hardware. We have shown the examples to implement ultrasound beamforming on Intel iGPU, DGPU, and FPGA. And we have shown there is a possibility to integrate algorithm acceleration and also AI inference on this heterogeneous compute system using Intel oneAPI and OpenVINO. So I think with this oneAPI implementation, we are very seamless and easy to support future Intel acceleration hardware as well. So that is all from us for this training session. Thank you for your time.